Alright, good morning. Welcome everyone. It's my honor to be the first speaker here today. My name is David and I'm going to talk about the MINIX 3 service layer. But first of all, let me introduce myself a little bit. I'm one of Andy's PhD students right now. I'm very close to finishing that up. Over the past 10 or so years I have been working on MINIX, not just as part of my studies, but also as a hobby project basically. And sort of over the years the MINIX 3 service layer has become my backyard. I just like hacking on stuff. So this is always been fun for me, and it's my honor to tell you a little bit about what is going on in the service layer right now, because the project that I'm working on is for better or worse, much of the activity that is going on right now here. So this is what I'm going to talk about. First of all, let me get a little bit of terminology straight so that everybody knows what I'm talking about. This is with respect to the software stack of MINIX. Then I will talk about the service layer evolution over the years. I will talk about some of the projects that I have been and am working on. And I will conclude, finally, I promised in my abstract to talk a little bit about how to contribute. I won't actually have time for that, but I will do it anyway. So let's get started. First with the terminology. As you know, MINIX is a microkernel system, and that means that at the very bottom of the software stack we have the microkernel. This is the only part that is running in kernel mode. And on top of that, there's a bunch of servers and drivers, or as we today call them collectively, services. And these implement all kinds of functionality on top of this fairly small microkernel. And together, this is the operating system. This is what you would find in a monolithic kernel on another system. And on top of that, we have user land, and this is very, very important, different from user mode, because the services are also running in user mode. This is user land, this is a bunch of utilities, and we have determined that, a couple of years ago, we determined that it's way too expensive, way too labor intensive to maintain our own MINIX user land. So now we're slowly switching over to the NetBSD user land. And on top of that, we also have a number of packages, also using NetBSD package system called package source, which adds actual functionality to the system, actual programs. And together we are also calling this whole thing user land. It doesn't really matter. So this is sort of an overview, and now in this talk I'm going to zoom in on the service layer. And I would like to take a quick look at the history of the service layer. And this is sort of what we started off with in 1987. I was 4 back then. The two blue circles that you see are the two servers that make up the service layer back in MINIX 1, which came with the first MINIX book, the operating system's design and implementation book. And these two servers are implementing much of the functionality at that time. We have a memory manager, MM, also takes care of a lot of process management, and a file system component, FS, that takes care of everything from file descriptors and open files to implementing a MINIX file system. 10 years later, the second edition of the book came out, and as you can see, not much has changed in a decade, which makes sense because back then MINIX was still an educational operating system, so it didn't make sense to have a lot of progress there. What did get added back then was the green circle, which is a networking service in my coloring scheme, and that was an optional TCP/IP stack called INET. Yet another decade later, the third edition of the book came out, MINIX 3.1 came with that book, and this sort of started the process of turning MINIX into an actual operating system, something that could be used for actual real-world purposes. And the biggest step that happened in that the development was that the drivers were finally taken out of the kernel, turning the MINIX kernel into an actual microkernel after all these years. Those are the red circles, and as you probably have heard, MINIX 3 has the ability to restart crashing device drivers, and for that we have an RS component, the reincarnation server. And in the meantime, the MM memory manager also got renamed to PM. So that was about 10 years ago, so now another 10 years forward we are looking at the current situation, and now it looks like this. So you can see that as part of the ambition of MINIX to be more than just something that comes with a book, there's a whole lot of progress right now. I think the most functional, the biggest improvement is the addition of the VM server, virtual memory server, which does paging. You see it in the bottom right here. I think the most structurally impactful change was the fact that the FS server that you saw earlier has now been split into a VFS component and an MFS component, and that basically separates the management of open files from the actual implementation of the file system. And with that change, we could also start adding other file systems next to MFS, and those are the purple circles here. And this color encoding scheme is actually in line with how the services are divided into directories in the source code of Minix today. So this is the current situation. I can't explain all of this picture, but I will zoom in on some things that I have been working on. And the first one is a new information server, and that's the MIB server that you see at the top. This is a project that I did a couple of months ago. And this basically goes to the question of how do we expose system information from the operating system to userland? And how do we allow userland to change settings in the operating system in order to influence how the operating system works? And this is, of course, something that has to do with the guts of the operating system itself. So this is something for which there has been no standard over the years. And that means that every operating system has developed its own solution. One particular use case here, and the use case of this story, is the PS utility, which, as you know, shows a list of processes currently active in the system. And in Minix, the PS utility ultimately needs to get information from process tables that are part of several services and the kernel. And in the traditional implementation of the PS utility, PS would simply get a copy of all those process tables and then parse them itself and get the information from there. And this is of course not exactly what you want, because that means that every time any of those process tables gets changed within the operating system, your PS userland utility breaks and you have to recompile it in order to update it and deal with the new format of the process tables. So, like all other operating systems, Minix has added a layer of abstraction there which solved that problem. And our first attempt was ProcFS. And this was a Google Summer of Code 2009 project for which I was the mentor. Back then we didn't know that we would be switching to NetBSD userland, so we modeled something based on Linux, and that was the ProcFS file system. And you've probably seen this on other operating systems. Basically, the information about processes and other things are exposed as files in a virtual file system. And the PS utility was changed at the time to make use of this ProcFS, and that solved the problem at that time. However, recently, we have of course been looking at importing NetBSD userland, and as part of that, we also wanted to import NetBSD PS. Not just because that was a logical part of it, but also because it turns out that a number of NetBSD scripts depend on how NetBSD PS works. So we could basically not just change the Minix version to be in line with that. That would have been useless, and we wanted to switch over anyway. But as it turns out, the NetBSD PS uses a completely different way of getting its information. Namely through the sysctl interface, or syscontrol interface. This is sort of the thing that the BSD uses in order to expose and allows the user to control system information. And this is basically an interface to a key value store, which is stored as a tree, and you can get and set values through this sysctl call. The keys are arrays of numbers, one per tree level, and this is sort of a numbering scheme that is in line with the management information-based style, which is just a sequence of numbers, each number going deeper into the tree. And those sequences of numbers then represent one key. Keys that are based on numbers are of course very inconvenient to use, so BSD is also using symbolic names for that. For example, 1.10 is actually called current.hostname, and that is the setting for the current hostname of the system. The values of those keys are integers or strings or opaque structures, basically. The whole thing is not persistent, and as such, most of the keys in the key value store are managed by the operating system, created by the operating system, and represent values that are actually useful for the operating system. However, it is possible for userland to create its own keys as well. And as it turns out, PS is actually using this interface in order to get the process information from the NetBSD kernel. So that raised the question, how should we then go about importing NetBSD PS? We have a NetBSD PS which uses the sysctl interface, and we have ProcFS that offers the actual information. So let me run through the options that we had basically. The first one was to change PS to use Procfest directly, and this was a terrible idea because that means that once we've imported this utility and then changed it once, and we would later like to update the PS utility to a newer version from NetBSD, which is certainly something that we want to do, we would have to redo the work all over again. So this was a bad option. Second option was to make use of the fact that PS uses an abstraction library, libkvm, to get the process information from the system. And we could replace this with a custom implementation on Minix in order to make use of Procfest. However, I seriously considered this until I found out how many other utilities are also using sysctl in the system. And that sort of shifted my focus from just getting PS to work to getting sysctl to work in general. And that meant that libkvm would not be a full solution to the problem that we were actually facing here. So, as for implementing sysctl, that still left a number of choices. One is to emulate the sysctl system call as a wrapper call in the C library, and based on that, make it use Procfest to get the information. That would have been a good idea, and I prototyped this, except that it turns out that if we do this, then performance for especially PS would be horrible because of a fairly big mismatch between how sysctl offers information and how Procfest would have to be used in order to get that information. And also, this would not allow us to have this global namespace that is editable by user programs. So this was ultimately also something that I rejected. Finally, that meant that we started looking into making sysctl an actual system call in the system. And then the question would be, in which service would we add it? Of course, one of the options would be to add it to Procfest, which already exposes information. However, in terms of implementation, there would be very little overlap between Procfest and the implementation of the sysctl call. And as a result, that basically resulted in a service doing two things. And that's also not something that we want, especially for resilience against crashes. So in the end, I decided that the best option would be to create a new service, and that service would just be the implementation of the key value store, as also found on NetBSD, and implement the sysctl service and offer that to userland. So that is what I did a couple of months ago, and that is now the MIB service based on the management information base style numbering. This has been merged, so this is available on the CD that you can get from the table outside. About 85 of the 800 keys that NetBSD offers by default are implemented right now, but those are by far the most important keys. So a lot of userland is now working. It's about 4,000 lines of code, and I've changed the Procfest implementation to make use of the MIB service rather than do the same thing in a different way, in order to eliminate redundancy of parsing those process tables. And I imported a number of userland utilities, not only BS but also sysctl, which is the userland interface to access that key value store. Also a number of other ones, and a personal note to Ben is that the old top is also still preserved, so we still have it. But I think more importantly, this new sysctl, this MIB service represents a way forward in order to import much more from NetBSD. Because, as I said, a lot of utilities use sysctl, especially also networking utilities, for example, netstat, etc. And by having this service, we now have a convenient way to create an implementation for the keys that are necessary to import those other utilities as well. And you can try it if you type sysctl-a on the Minix 3.4 system, then you get an overview of all the keys and their values. So that is the first project. Moving on to the second project, which is about library-based file systems, and here we are zooming in on the MFS component, so the Minix file system component, and services like those, and they can basically be described as disk-backed file systems, as in file systems that actually use storage to save their stuff, as opposed to, for example, Procfest, which is just a virtual file system. Now, in this area of disk-backed file systems, we have not seen so much progress, at least not as much as we hoped for. In 2006, as you saw in the figure, we split up the FS service into VFS and MFS, and that allowed new file systems to be created at the time. But 10 years later now, we only have two more of disk-backed file systems, ext2 and ISOFS, and those are very useful, but it's not really the success that could have been there based on that split. So what is the problem here? And I think it is basically a problem that it's pretty hard to write a file system service, and that is mostly because of all sorts of POSIX requirements that have to be implemented for all the file system calls, and all sorts of error handling that you really have to get right. For example, implementing the rename the assistant call is really not something that is very pleasant. EXT2 and ISOFS, as a result, simply started out as copies of MFS, which is in essence a nightmare in terms of maintenance, because that means that well, we've had to fix the same bug in 3 different implementations on several occasions. So that's really not great for maintenance. So what can we do to improve on this? Not just make it simpler to write new file systems, but also to help in the maintenance of the current ones that we have. And there has been some progress to break down, to carve off some of the functionality from the MFS and other file system implementations into libraries. So that has been some progress, but those still don't get at the heart of the file system. And that means that we still have to find some way of solving this. And I think that the key to solving this lies in 2 observations, and those are by no means new, but I think they are useful for us right now. First of all, file systems are graphs. They have nodes and edges, essentially, and they're built up from that. And second of all, most file systems today have Unix origins, which means that the nodes of the graph are represented as inodes, and the edges of the graph are represented as directory entries. And in terms of file system operations, these can all be broken down into a series of node and edge operations in those graph, this graph environment, if you will. So, for example, to create a file, you have to allocate a new inode, which is a node operation, and you have to create a directory entry for that inode, and this is a edge operation. And as it turns out, you can indeed break down all of these operations this way, and that means that basically what you get is graph-level logic, so the logic that makes use of those node and edge operations, that is fairly generic and can actually be shared between file systems. And that means that we can actually reuse that part between file systems. So then, if we follow these principles, the file system starts to look like this. You have a node layer, and this node layer implements the inodes, and this will always, of course, be specific to the file system that you're implementing. So for MFS, this is going to be the MFS node layer. On top of that, you have an edge layer, which takes care of the directory entries, and this is already something that could potentially be shared between multiple file systems, as long as they have the same format on disk for directory entries. But most importantly, on top of that, we have a graph layer, and this graph layer is basically a generic part which implements all those file system operations based on the nodes and edge layers below. So, based on these observations, I've made an implementation, a prototype. This is something that fell out of research that I've been doing, a new file system called TwinFS, which is a crash-consistent file system layout. And I built a prototype along the lines of what I just described, and this is sort of the result in terms of lines of code that you see. And the most important part here is that the graph layer of about 3,000 lines of code is pretty much generic, and it would be possible to reuse this in other file systems as well. I have not merged the 20FS yet, so this is sitting in a branch somewhere. But it is, I think, the way forward here, and of course this will involve also modifying the existing other file systems to make use of this graph layer. But I think this is sort of the way forward in terms of making it easier to write file system services, and also making it easier to maintain the current file systems that we have. The last thing that I want to talk about is the network stack, and this is something that came up in a conversation a couple of weeks ago with a bunch of people that are here today. Well, this is sort of the network stack in the figure that you see here. We have a TCP/IP stack called INET, and we have a Unix domain sockets implementation called UDS. And INET of the two is the one that, of course, uses Ethernet drivers below it. And this is sort of the story of well, how a project can sort of get out of hand. When we talked about it a couple of weeks ago, it was sort of like, yeah, let's see how we can add IPv6 support, because I think that IPv6, I think you all agree that IPv6 is the future, so we have to in some way deal with this. And this is sort of like, yeah, there's a couple of other things that could also be done if when we're working on this anyway. And so now this is turning into 3 sub-projects, and the first of them is adding support for native BSD socket calls. Second is actually replacing the TCP IP stack with something that supports IPv6. And finally, we have to revisit the packet level, I think. So I'll dedicate one slide to each of these. First of all, the native BSD socket API. Right now, the 2 network services, the green circles that you saw earlier, INET and UDS are character drivers. This is kind of interesting. The first time I saw this, I thought, character drivers. But the BSD socket API, which you are familiar with in terms of calls like socket, bind, connect, send to, accept, etc. Those are implemented as wrappers in libc, and basically translating those BSD socket calls into calls that are usable by character drivers, mostly IOTA calls. This approach has a couple of problems. I don't really have time to get into this, but there are good reasons to basically get rid of this. And the solution is simple, namely we have to turn these BSD socket calls into system calls, actual system calls, rather than character driver calls. So that means that INET and UDS would become socket drivers rather than character drivers. So this is a completely new class of drivers in the system. This would be managed by VFS, and VFS would simply take those BSD socket calls from userland and forward them to the right socket drivers, which is actually a lot harder than I make it sound right now. But I have an implementation of this right now, at least of all the infrastructure that is necessary. So everything going from libc to basically the API that is to be used by the new socket drivers. And I'm in the process of converting UDS to be a socket driver. Converting INET to this new socket driver model would be much harder, but that's where I sort of get to the next part, because we may not have to if we want to replace the TCP IP stack anyway. So I think that right now, the way that we see it, these are the most important requirements for a new TCP IP stack. First of all, of course, this was the original purpose. It has to come with IPv6 support. Second, we also would very much like it to be interface compatible with NetBSD, which means that we would be able to import all networking utilities from NetBSD, like the HCP and stuff like that. And third of all, it also has to be maintainable, and that means that making all these modifications to the current stack ourselves is basically not an option. So over the years we've been discussing this and discussing possible options here, and this has sort of given us 3 options over the years. One would be to import a more recent version of the same INET server from, well, its home basically, which is MINIXCon. We'll be talk about that later today. However, this would, I think, not give us the interface compatibility with NetBSD that we are looking for. The second option would be to, well, let me put it this way. We already have a second TCP IP stack implementation, which is based on lightweight IP, which is a TCP IP library, basically. However, the wrapper code, which makes that library work on Minix, is not exactly of production quality code. And that basically means that it's not an improvement over the current situation. But we could re-implement those wrappers and use lightweight IP as the basis of the actual TCP IP stack to go with that. That would require some work, but it's something that could be done. Third option would be to use rump to extract the NetBSD TCP IP stack and put that into its own service. And unfortunately, this is something that, even though it would be very cool, there are a lot of unknowns associated with that. We don't have rump working right now, and we don't know how feasible it would be to do that. So right now, I am leaning heavily towards option 2 to use lightweight IP to and re-implement the wrappers in order to work with the new socket driver abstraction and with the NetBSD interface. Finally, if we're looking at the TCP IP stack anyway, then we might as well look at what happens below it. And that is sort of a story of preparing for the future, and this is sort of where I also don't really know what I'm talking about. In this sense, I don't know if we want support for other protocols next to TCP IP. I know that there's a couple. I don't know if any of them are still relevant for people. If there's others that are coming up these days, stuff like Apple Talk has been around for a while, of course. Also, non-Ethernet devices, I don't know if they're out there these days, if it's useful to support them. And maybe we want support for a firewall. In that case, how would that look? How would routing look? Stuff like that. And basically, I hope to learn a lot from other presenters here today. I know that there's a couple of people in this room that know much more about this than I do. So I hope to sort of establish somewhat of a picture that we can use to go into the future with this part of the whole network stack. To conclude, the service layer is, as you've seen, evolving rapidly, and this is a good sign in the sense that Minix is growing up and it's catching up very fast. But this also sort of creates growing pains. We have to be careful not to make things too difficult for ourselves by just throwing in functionality. So we have to use proper software engineering in order to go forward. And this also means that we have to properly restructure things in a way that actually works for us. And we have to make sure that we eliminate redundancy, make sure that there's not too many copies of the same code, because that just creates more difficulty for us. And that is sort of that can be summarized in a more general statement that given that there is not so much manpower for Minix to be maintained, we really have to focus on the maintenance aspect to get things right so that we don't waste time on working on the wrong stuff, basically. And that was my talk, so I promised to tell you a little bit about how you can contribute, so this is why I'm totally running out of time now. But we need your help. The project like this, we are going to have a problem if we don't have more contributors. So if you are at all interested in contributing in any way, then you're more than welcome to do so. This can take the form of code development. For example, an easy start that we always recommend is to port more of NetBSD's userland to Minix. Another good start would be writing a device driver. There will be a talk about that later today as well. And there's a lot of functionality that can be filled in. Other activities, there's also, if you're not so much of a coder or not so interested in that, there's other activities that you can do as well. We have a huge documentation problem. A lot of documentation is outdated, a lot of it is missing, and we would very much like people to go over that and correct things. PR work is also something that we are going to need people for. Right now, Andy is the only person who actually does PR work, like organizing this conference. But there's more day-to-day stuff that we have to do as well, like updating Twitter, that kind of stuff. And finally, if none of these things are sort of your thing, then you can always just test Minix. Just install the ISO, try it in a virtual machine, see what kind of problems come up, try some packages, and report issues to us so that we can look into fixing them. If you would indeed like to contribute, then these are sort of the main resources. There's a lot of information, as I said, some of it is outdated, but there's also some actually very useful stuff. And things like wish lists, to-do lists on our wiki. We use GitHub for the source code, for bug reports, and for submitting code, basically. So if you want to file a bug report, but also if you want to work on solving a bug report, then this is sort of the place to go. Finally, we would be happy to help you out. There's two places that you can basically contact people with a little bit more experience with Minix. One is the Newscope, and the other one, we are very active on IRC as well. And that is my talk. I'll leave you here with my email address in case you want to contact me. Also, I'm just mentioning that I'm looking for a job right now. Other than that, thank you for listening, and well, if there are any questions, then I would be happy to answer them.
So we have time for a couple of questions.
You mentioned file system layer and how its architecture. I'm a little bit missed it, and didn't understand. Can you please return and maybe tell me how is hard going to be to integrate the logic of the current system with maybe some specific feature for a drive? You know that previously we got this drive, and now we are moving to SSD. SSD is quite perfected. There is a lot of interesting stuff like parallelizing, and will it be easy to integrate them in this thing?
That is a great question. So let me just repeat it because I'm not sure that the audio is coming in. Basically the question is how can we add support and does it work with this model to add support for other devices like SSDs and their features?
Like it's only support. I mean, the other devices, they can have some specific logic inside of it, and not maybe features. And to work with these features, it would need integration, maybe in graph, maybe in file system logic. Maybe there will be different file system. So will this architecture support this integration?
In principle, I think that if you want to support all the features from SSDs, then these days, to a large extent, of course, SSDs are usable as normal hard disks. That's how they are sort of made. But indeed, in order to get more out of SSDs, you need more support on the file system side of things. And this is indeed something that could be implemented in part of this. I think most of this would be constrained to the node layer in this case. So that would be the particular implementation of the file system format. So for example, you could have a file system that is optimized for using SSDs or flash devices even, whatever. And that would be, right now, that would mean that you have to create a new file system that uses those features. I think that the graph layer would remain unchanged, basically. So that is not something that will have to change in order to make use of those features. It's mostly related to how do you access stuff on disk, how do you position stuff on disk, how do you file requests to the disk driver. And that's pretty much all constrained to the node layer. So maybe it's also good to mention that we've actually done some research in this direction in order to build a better storage stack, which actually allows you to do this in a completely different way. This is the Loris storage stack. If you look at my name and the name of my colleague Raja Apaswamy, you will find a whole lot of papers about how sort of the next generation of storage stacks would be able to deal with this problem in a much better way. The problem right now is that it's a lot of engineering effort to actually put in a storage stack like that into a system like Minix, something for which I simply don't have time. So right now that is sort of staying in research, but I do believe that that is sort of the way forward in terms of a larger storage stack redesign, which also would be able to incorporate all those kinds of features for particular forms of hardware.
Okay, I think the time is up, and I'd like to sort of stay on schedule if possible. So again, thank you very much.